Let's discuss the third effect of GOC, the hyperconjugation. These are of two types, plus H and minus H. So we mainly discussed more about the plus H effect. What is this? Let's take an example. So to understand what is hyperconjugation, let's take an example. So this is a carbon with positive charge and it is electron deficient. So to get this electron density, this hydrogen bond will break, or maybe this, or maybe this, or maybe this, or maybe this, or maybe this. These are all alpha carbons, and these are called alpha hydrogens. So to get the electron density from these carbon, so the resonating structure will like this: C double bond C, H and H, and this hydrogen will remove, and this electron density will go from here to here. So it is a type of donating effect in which electron density come and goes, and again this bond is unstable and come back from here to here, and this will take electron density back from formation of this bond, and it will be remain hydrogen. So hyperconjugation is also called as no bond resonance. It's a type of resonance in which no bonds are required, and is also termed as sigma bond resonance. These are all the names of hyperconjugation, and it is discovered by Baker-Nathan effect. That is one of its name. So these are some conditions which need to be required to perform the hyperconjugation. So first, there is an electron deficient molecule must be present, just like that, and in its alpha position a alpha hydrogen has to be present. So in hyperconjugation, in chemical term, we can speak that the transfer of electron density from sigma CH bond to the empty p orbital of carbon is performed. So this is called hyperconjugation. And if you talk about the stability of this molecule, so stability of carbocation is directly proportional to the number of alpha hydrogens. So this is also an important point which we will discuss here. So hyperconjugation can also be performed with the help of free radical, just like here, a free radical and a positive charge, or we can say a carbocation, and an empty pi orbital which is present in alkenes. Hyperconjugation can also be occur in this. So the only condition is in carbocation, the sigma CH bond is transferred from the electron density from sigma CH, this sigma bond is transferred from here to the empty p orbital, and this is also called plus H hyperconjugation, and it is also occur in the case of free radical because it is also an electron deficient species. So electron density move from sigma CH to empty p orbital of empty p orbital. It is also a plus H hyperconjugation, and an alkene, just like here, also have an empty pi star orbital. So here in electron density from sigma CH is transferred from sigma CH to empty pi orbital. It is also a plus H hyperconjugation. So there are some examples. There is one question in which of the following compounds show hyperconjugation. So to perform hyperconjugation, we first need to know about the first molecule. Here we have a double bond here, and it is an sp2 carbon. So this is not the condition for hyperconjugation. The next is a carbocation, and in alpha position there is nitrogen. So nitrogen is not carbon, there is only be carbon for performing hyperconjugation. So it is also not possible. Here a carbocation with oxygen. So oxygen is also not carbon, so it is also not going to perform hyperconjugation. And another one is carbon with CH3. So this is an ideal condition which has alpha carbon and alpha hydrogens. So here the electron density will move from sigma CH bond to carbon empty orbitals. And here also it is not possible. So this is the D option will be right here. So there is one question according to which the question is asking what is the order of these three molecules in case of hyperconjugation. So we know that the isotopes of hydrogen. So here we know that the isotopes of hydrogen are deuterium and tritium. So in case of mass is increasing, in tritium it is the highest mass of hydrogen. So the bond length if the mass is increasing, then bond strength is also increasing. Mass increases, the bond strength also increases, and the least and easily breakable bond is CH bond. And we know that in hyperconjugation the order of plus H is the requirement to break easily bond. So the carbon hydrogen bond easily breaks, so the priority order will be this: carbon hydrogen first, then the deuterium, and then the tritium. So with this example we will make an statement or a note in which if mass is increasing, then the bond distance will decrease and the bond strength will increase. So mass is directly proportional to the bond strength and inversely proportional to the bond distance. Now let's discuss about the application of hyperconjugation. So let's discuss about the application of hyperconjugation. As you can see, it is used for the stability of carbocation and stability of free radical and alkenes to determine their stabilities. It is also important for finding the heat of hydrogenation, dipole moment, and electron density in a ring. So these are all the applications. Let's discuss one example from the stability of carbocation. As you can see here, if the number of alpha hydrogens is more, then this is more stable and it is donating with plus H and also with my plus I. So this is more favorable as compared to without any methyl group in carbocation. So the stability of carbocation directly proportional to the number of alpha hydrogens, and stability of free radical is also directly proportional to the number of alpha hydrogens. So now let's discuss another example here. Let's count the alpha hydrogens here. 2 alpha hydrogen are present. 2 alpha hydrogens are present here and 2 here. So total of 4 alpha hydrogens are here. And if we take this carbocation, here 1 alpha hydrogen and here 2 alpha hydrogens are present. So 3 total, and here 7 as compared to 1 methyl group 3, and these 2 and these 2. So 3, 4, 5, 6, 7 alpha hydrogens. So we know that the stability of carbocation is directly proportional to the number of alpha hydrogens. So C is more stable as compared to A because of 4, and the least stable is 3. So this is the stability order of this. Now next we discuss about the stability of alkene. So if we talk about the stability of alkene, then let's take an example here. With this alkene, 4 methyl groups are attached from there. Then, and in B second structure, 3 methyl groups are attached, and here 2 methyl groups, and here in same the 2 methyl groups and one, and the no methyl groups is here. So if we talk about the stability of alkene, then we count the number of alpha hydrogen first. So number of alpha hydrogen here is 12 alpha hydrogen, here it is 9 alpha hydrogen, and here it is 6 alpha hydrogen, and it is also 6 alpha hydrogen. So to determine between these two, we first need to know whether who is more stable, as is we are discussing stability here. So we know that trans structure is more stable as compared to cis structure due to repulsion factor. So this is more favorable or more stable as compared to cis alkene. So the stability order of this is that. Now let's talk about the heat of hydrogenation. It is also an application of this. So we know that heat of hydrogenation is the number of pi bond. As to determine whether the heat of hydrogenation is more or less, we first need to count the heat of hydrogenation is directly proportional to the number of pi bonds. And the second, we use the priority order. First we need to, first step is to count the number of pi bonds present in the molecule. After that we check their stability. If it is more stable, then it is least likely to be have the higher heat of hydrogenation. So let's take an example here. So in this molecule, as you can see, this is A and this is B. We need to find the order of heat of hydrogenation. So first we check with the number of pi bond. So as we know, here in the same molecule, the number of pi bond is same. So now we go to the stability of this molecule. So we know that who is more stable as compared to B is more stable as compared to A. No, A is more stable due to the presence of 6 alpha hydrogens. And we know that the number of alpha hydrogen is more here, so it's most likely to be more stable as compared to this. So in this question, the order of heat of hydrogenation is, in A molecule there are two number of pi bonds. The number of pi bonds is 2 and here 1. So heat of hydrogenation is in A more as compared to B. In next question, the order of heat of hydrogenation is, in first molecule there is a benzene ring and one pi bond is present. In second option there is a conjugated alkene is present, and in third option there is a double bond but they are not in conjugation. So if we talk about the stability, now let's talk about the order of heat of hydrogenation. So first we count the number of pi bonds. So step 1 is number of pi bonds. So B and C have 2 pi bonds, so they will come first and A will be the last one, and because of the number of alpha hydrogen, and if we compare these two, they have the same number of pi bonds. So we go and check their stability. So we know that B molecule, due to its conjugated alkene, it is most likely to be more stable as compared to C. So we know that stability is inversely proportional to the heat of hydrogenation. So C is more HOH than B. So this will be the final order of HOH. Now let's talk about another application of hyperconjugation, that is dipole moment. So to explain this, what is a dipole moment? It is nothing but the polarity difference between the molecule. So let's take an example with the dipole moment here. This oxygen and this is carbon here, and if we put poles in this molecule, then it, due to oxygen more electronegative, So negative charge will come in oxygen and carbon get the positive charge. So to stabilize this positive charge, there is hydrogen, so it will be not that stable, and this methyl group will donate and perform plus H. So it will make this polarity, the dipole moment, more stable. So we can discuss the stability of dipole moment with this. So B has more dipole moment polarity than A because its polar form is more stable by hyperconjugation. Now let's talk about the electron density in the ring. We can also discuss the sixth application, which is the electron density in the ring with the help of hyperconjugation. So let's take an example here. As you can see, a benzene ring is present and a methyl group is attached here. So as you can see here, in hyperconjugation, the sigma CH electron density is transferred from sigma CH pi bond to pi star of empty ring. So it will make the ring more stable, and this is a neutral ring, and this is an electron withdrawing group. This chlorine will take electron density from ring and making it more unstable. So this is called minus H effect and this is plus H effect. So if you talk about electron density order, then A will be higher than B because of the neutral nature, and C will destabilize the ring. Now let's talk about the third effect, which is resonance. So what is the resonance? It is the delocalization of electron density from one bond to another. For pi bond, maybe it can be of double bond, just like that, and will form a resonating structure of plus charge here, this, and negative charge here. And if we talk about a lone pair, it can be sulfur, oxygen, nitrogen. So the lone pair is transferred here, and this type of motion is also possible here. So nitrogen will get the positive charge because it is neutral, and after this this bond will get negative charge, and it is same for anion also, and due to which it is not getting any positive charge because it's a charged species, and it will get neutral after transfer of charge. So here we cannot do this. If we can do negative charge is present, then we can delocalize it with, and cumulated alkene like structure can be formed. And we can also, if a negative and a positive bond are present, then we can make a bond in this position, so bond formation will take place. This is a resonating structure. We cannot put the double bond, electron density double bond from the negative in opposite direction, so this is not possible. And we cannot put the positive charge to the opposite direction of the negative, it is also not possible. Now let's make it a 2. What is if let's take an example of localized or delocalized. What is localized and what is delocalized? In we study this in resonance. So what is localized mean is that localized means local. The transfer of electron density is not possible here. So what are the example in which electron density cannot be transferred? So these are called localized group. Just like if a nitrogen group and free radical is present, and just after that a pi bond is present, so electron density cannot be transferred here. So this is a delocalized bond. So this is a localized bond. Delocalized means it is not localized, it is not unstable, it is in the motion. So delocalization of electron can easily be done in case of nitrogen, and if a single bond is present and then alternative or double bond is present, so electron density can be transferred here, and this will go here, and resonating structure can be formed here. So localization and delocalization can help us to make the resonating structure. Here in third example, an ammonia and a nitrogen group here the nitrogen free radical is localized in nature. And in delocalization section, if a pyrrole ring which is not attached anywhere, then this is in motion. So this resonating structure is possible. So this is called delocalization. Nitrogen will be, the pi bond will go here, this bond will go here, and this is here. So in here, in fifth case, a nitrogen group is attached, and if a lone pair is present or any negative charge is present here, then if we cannot put this in this direction because it is in the bridgehead position, and the double bond that form here is unstable, so we cannot put this here and make that this type of delocalization of electron density. So this was explained by Brad's rule, according to which double bond at bridgehead position is unstable.